So welcome to the next topic in the electromagnetism unit, the forces on currents. So the learning objectives for this unit are that you should understand there is a force on charged particles when they move in magnetic fields as long as they are moving, and that motion is not parallel to that magnetic field. Understand that a force is exerted on a current carrying wire in a magnetic field, and how this effect is applied to simple DC electric motors and loudspeakers, so we'll use those as two examples. Use the left-hand rule to predict the direction of a resulting force when a wire carries a current perpendicular to a magnetic field. Okay, so you've had the right-hand grip, now it's time for the left-hand rule. And finally, describe how the force on the current carrying a conductor in a magnetic field increases when the strength of that field, with the strength and the field and current. Okay, so we're going to look now at what happens to electrical charges in magnetic fields, because they may have forces being exerted on them.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong, concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here we're going to start turning it up, and you can see it's starting to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. So if I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion going right back to where it started. And if I turn the magnetic field back down to zero, straight again. So there's direct visualization of the circular motion of charge in a magnetic field.
So what's happening? Well, essentially what's happening is that the magnetic field is exerting a force on the electrons. So in a magnetic field, if the field is perpendicular to the charged particle, it will exert a force on that charged particle, either moving it up or moving it down, depending on the charge, whether it's negative or positive. The other important thing to note, though, is that in this particular example here, the magnetic field is moving into the page from north to south. So, into the page, because the arrows, okay. But if the charge was parallel, or sorry, not the charge, the magnetic field was parallel to the motion of the charged particle, then you would see no force being exerted. It has to be at right angles, okay, perpendicular to the motion of the charged particle. And also the charged particle has to be moving. Okay, stationary charged particles do not have the forces being exerted on them. Okay, so just in summary, the charged particle changes direction when it moves in a magnetic field as long as the motion is not parallel to the field. Okay, so a change in velocity, a change in direction is acceleration, and that requires a force. Okay, force equals mass times acceleration from your force units last year. And the magnetic field is therefore exerting a force on the charged particle. It's changing its direction, it's changing its velocity. So what does that look like with currents in a wire? Well, that's known as the motor effect. So a conductor, or say a metal wire, carrying an electrical current is placed in a magnetic field, and the conductor may experience a force. Okay, so here we have two bar magnets close together. Okay, they're going to be a magnetic field, a uniform magnetic field between them. This is called the motor effect. If you place so you've got the magnetic field uniform between the north and south poles. If you place a conducting wire which is carrying a current, so the charges are moving between the magnetic field lines, okay, you break the magnetic field lines. Remember, it's going from plus to minus, okay? It's going to exert a force, okay, and push it up. Now notice, of course, that the current is moving from plus to minus. We are using something called conventional current when we're talking about the movement of electrons. Okay, so you would think that it would be going from negative to plus. Okay, electrons move to the positive. Okay, electrostatic attraction, but we are using something called conventional current because before we knew that electrons were the charge carriers, we thought that the positive charges were the charge carriers, and we've kind of stayed with that. So in conventional current, the charge or the current moves from plus to minus. Okay. So the force itself increases if the strength of the magnetic field, which we call capital B, is increased. Okay. The current I, which we've used before, is increased, or the length of the wire is increased. And there's an equation which we'll learn in the next slide, but the direction of the force is reversed if either the direction of the current or the direction of the magnetic field is reversed. So rather than the last example, the wire being pushed up, it would be pushed down. Okay, and the conductor will not only experience a force if the electrical current is moving perpendicular to the magnetic field lines. If it's going to be parallel, then it's not going to experience a force at all. Okay, so you can calculate the force if the magnetic field is right angles, perpendicular to the current. The force F on the current is given by the following equation. F equals Bil, B-I-L, where B is the strength of the magnetic field in something called a Tesla. I is the current in the wire in amps, A, and length is or L is the length of the wire in magnetic field in meters, M. Okay, so we've looked at the right-hand grip rule in previous lessons, and today we're going to introduce another hand-based kind of model to help us understand the electromotive force that's being exerted on a conducting wire carrying a current, known as the left-hand rule. Okay, so this is the left-hand rule. Okay, so get your left hand, and it's basically going to be like a gun with the ammunition on the poking out of the gun. Okay, so you've got the thumb is going to be the force being exerted on the wire. Okay, your ring finger, as it were, is going to be the direction of the current, and your second finger is going to be the direction of the magnetic field. Of course, remembering it has to be perpendicular in order for it to exert a force. So there's two things you have to note. Okay, the magnetic field direction is always from north to south, and the other one is that we're using conventional current, so the current direction is from positive to negative. Okay, so let's now look at some examples of what direction is the force. So question 1, force direction. So again, you get your left hand out. Okay, left hand out. Remember that dot means that the current is coming out of the page. Okay, the arrow is coming towards you, and cross means that the arrow is going away, so it's going into the page. So in this particular example, your ring finger is going into the page. It's going from north to south, so we have to kind of flip it around. So the force is going down. Okay, Force is going down. Current direction in question number 2. So again, north to south. So your second finger, left hand, north to south. It's going to be going down, the force. Okay, so the force is going down. So to kind of do that, okay, it means it's going to be going out of the page. Okay, a bit of yoga there for you. Wow. Okay, north-south poles. Okay, so it's going out of the page. Okay, so your ring finger is going out of the page for you. The thumb is going up, so the direction must be going from north to south. So that means the north pole is going to be on the left-hand side. Okay, cool. And question number 4, the direction of the forces. So you've got 2 wires. This could probably be, this is an example of, say, a loop within a magnetic field moving up and down. Okay, so for the first one on the left, it's going out of the page, north to south, so the force must be going up, and because it's going to be the opposite direction, therefore, for the other one, and that's kind of the example of the way a electric motor works. Okay, opposite directions. Excellent. Okay. Okay, so to finish off, we're going to look at 2 useful examples of this motor effect, which we looked at actually in that last question, in the last slide, because if the current's going in opposite directions, you're going to get one side of a loop going up and one side of a loop going down, which is essentially how an electric motor works. Okay, so in a motor, the electric current flowing around the coil of the electric motor produces oppositely directed forces on each side of the coil, which we saw in the last question. Okay, so opposite directions, one's going up, one's going down because of the direction of the current. These forces cause the coil to start to rotate, okay, move, and every half revolution, the split ring commutator causes the current in the coil to reverse, otherwise the coil would stop in its vertical position. Okay, pretty much it's saying it would just be stuck in the middle. This guy here allows the change of direction using AC, going from plus to minus to plus, changes the direction of the current, therefore changes the direction of the force on each component of the loop. So now instead of going up, the part of the loop on the left hand side will start to go down, and vice versa for the southern pole. Okay, so this is what it looks like. So brushes in contact with the split ring commutator, current flows through the motor coil, and forces exert a clockwise turning effect on the coil, which we see with my advanced PowerPoint animation. Okay, there we go. But when it ends up in its vertical position, the loop, the brushes lose contact with the split ring commutator, okay, which you're seeing here. Okay? Contact brushes lose contact. So current no longer flows through the motor coil. The coil will continue to rotate clockwise due to its momentum, which you probably learned in your first topic. Okay, this causes the brushes to regain contact with the split ring commutator, and the current flows through the motor coil, but now this time in the opposite direction. Therefore, the forces exert a clockwise turning effect on the coil now rather than an anti-clockwise turning effect. There we go. Back again. So again, this continues, and now continuing to rotate in the clockwise due to momentum. And there we are. So this is the diagram of a model electric motor, which we hopefully will be able to play with. And we're going to try and model, or actually create, some little electromagnets in the laboratory. Okay, so as you can see, you don't tend to have the commutator here much. Okay, essentially it's a wooden block with coils around the slot, so they form a current, they get then repelled by the appropriate magnet and cause the rotation, producing the electromagnetic force. Okay. The final example is a loudspeaker. So the sound signal consists of an alternating current supplied by an amplifier. Okay. The current flows through the coil of the loudspeaker, as you can see from the diagram, and due to the motor effect, the magnetic field around the coil causes the coil to vibrate in step with the AC current. The coil causes the diaphragm, the speaker cone as it were, to vibrate in step with the original sound signal. And the diaphragm causes the air to vibrate and so produces a sound wave, which we know from, which you will learn about more next year when we look at waves. And that, at the moment, is all you need to know about the motor effect and how charged particles interact with magnetic fields and how magnetic fields interact with charged particles.